Now, in order to work through this, I want to see if I can separate the variables, and that's really going to be, in real life, the first thing you look for is, can you separate the variables? And this will make a lot more sense when you see more complicated differential equations that are somewhat more tedious to solve. That if you can separate the variables, then it becomes an integration problem, and not necessarily a big deal. So that turns out when you're applying differential equations, it's the first thing you look for. Can I separate the variables? We can in this case, but I need to combine these fractions first. So 1/4 is 25 over 100. So combining, I've got 25 minus y over 100. And I'm going to multiply both sides by dt and divide by 25 minus y. So by doing a little bit of algebra here, I've got dy over 25 minus y equals to dt over 100. So I've reorganized the differential equation. I have a differential on both sides. I have the y's separate from the t's. And now I'm going to integrate, because I can do that. Once I have the differentials separated, we can integrate this thing. So what happens when you integrate here? Well, we're going to get a logarithmic form. It'll be negative natural log, absolute value, 25 minus y, equals to t over 100 plus a constant. So you can verify this. Take this derivative. It's 1 over 25 minus y. The chain rule, we multiply by the derivative of 25 minus y, which is negative 1. I need that negative to cancel. So this works out. This derivative will get you back to this integrand. And I'm going to kind of go fast on some of those integrations here, because I know you've had quite a bit of calculus, a year's worth of calculus, and so these integrations hopefully are not always going to be a big deal as much. Technically, in this case, I really don't need those absolute values, because I can't have more than 25 pounds of salt in this tank. In other words, 25 minus y will never be negative anyway, so I don't have to worry about a logarithm of a negative. Now I'm going to transfer the negative to the other side. So I've got natural log of 25 minus y equals to negative t over 100 minus c. And I'm going to cancel the logarithm just like we did before by making it an exponent of e. And so this cancels. I have 25 minus y equals to, and here we go again. I can split this up into e to the negative t over 100 times e to the negative c by using the rules of exponents. Well, e to the negative c is a constant. I'll just call that c. So I'm going to rename my constant like so. And then when we solve for y, I need to erase to make room for it. We're going to get a function here which solves our differential equation. So I'll put y over here, I'll subtract this, and I've got y of t is equal to 25 minus c e to the t over 100. There we go. So now this is exactly the kind of function I predicted. Okay, and not surprisingly, it goes like this, because it's 25 minus an exponential function. We'll see that that's what it turns out to be. It's approaching 25 pounds asymptotically. As t goes to infinity, let's see, minus t, sorry, negative t. As t goes to infinity, I have e to the minus t over 100. That goes to 0. And so this part, don't forget that negative, I forgot it, goes to 0. And so as t goes to infinity, the limit is 25. All right, now I have two constants here. I have c and t. T is related to the rate of change, and No, it isn't. T is time. Is time. But the C, I think we can get that by looking at the initial conditions. You know, we start off with, what, 5 pounds? We start off with 5 pounds, and so the initial condition was 5. And I better change my pen here, it's getting pretty dull. Hopefully that's a little darker. Alright, so y at 0 equals to 5. So if I plug that in here, I got 25 minus c e to the 0 power. And because e to the 0 is 1, then you can see that 5 equals 25 minus 20, c equals to 20. So my function describing the amount of salt at time t is 25 minus 20 e to the negative t over 100. Now the last question was how long before there are 20 pounds of salt in the tank? Alright, so how long before there are 20 pounds? I'm going to have to set this function equal to 20 and solve for time t. So I'll set this equal to 20 and we'll start solving. I'll subtract 25 and divide by negative 20. So I have e to negative t over 100 is equal to, let me see, subtract 25 again, negative 5 divided by negative 20 is 1/4. And to solve this, I'm going to need to take the logarithm of both sides. So I better get another blue pen. I think my blue pens are getting kind of weak here. I may have to switch to black. So the natural log of e to the negative t over 100 is the natural log of 1/4. Now, if you're pretty up on rules of logarithms, natural log of 1/4 is the negative of the natural log of 4. Now that's purely optional, but I wanted to throw that in there just to kind of remind you of a rule of logarithms. And so the log of reciprocal is negative of the logarithm. Natural log of e cancels, so I have negative t over 100 equals to negative natural log of 4. So when I'm solving this problem, the negatives will cancel, and t equals to, 100 times the natural log of 4. Okay, so 100 times ln 4, natural log 4 is 138.6, about 138.6. So, what was that describing? Oh, that was how long it takes before there are 20 pounds of salt in the tank. So, let's write out the answer to that. There will be 20 pounds of salt after about 138.6 minutes. Alright, so we have solved the problem completely, the well-stirred tank problem. And it was, I wanted you to see this application of differential equations. Rate of change translates to derivative, and this problem was a separable differential equation. I'm going to do more separable differential equations here in a moment from the textbook. And but anyway, I just thought this was a nice way to introduce separable differential equations.